Some illustrative incompressible viscous flow. Incompressible inviscid flows do not satisfy the no-slip condition. They slip at the wall but do not flow through the wall. To look at fully viscous no-slip conditions, we must attack the complete Navier-Stokes equation, and the result is usually not at all irrotational, nor does a velocity potential exist. We look here at three cases: flow between parallel plates, due to a moving upper wall. Two, flow between parallel plates due to the pressure gradients. Parallel plates due to the pressure gradient. Flow between concentric cylinders when the inner one rotates. Flow between concentric cylinders when the inner one rotates. The inner one rotates. Other cases will be given as problem assignment or considered in the chapter 6. All flows in this section are viscous and rotational. So in this section, all flows in this section are viscous and rotational. The first incompressible viscous flow type is flow between a fixed and a moving plate. Flow between a fixed and a moving plate. It's called Couette flow. This is a typical flow in mechanical engineering. Consider two-dimensional incompressible plane which run on equals to between parallel plates at a distance 2h as shown in this picture. We assume that the plates are very wide and very long, so that the flow is essentially axial and the x direction u is not equal to 0, but we have two components of the vector velocity equals to 0. The present case is in this picture where the upper plate move at a velocity v in this picture. But there is no pressure gradient. Neglect gravity effects. We learn from the continuity equation that for an incompressible flow, with this assumption, we have only one component in the continuity equation equals to 0. So we can write the u equals a function of only. Thus, there is a single non-zero axial velocity component that varies only across the channel. The flow is said to be fully developed. Substitute u into the x component of Navier-Stokes momentum equation, which is rho for a incompressible flow the dissipation part plus so from previous quantity is equals to 0, and we have also v equals to 0. Two parts is eliminated from the left hand side, and in the right hand side also this part is pressure gradient is also equals to 0, and the weight is negligible. The only case which is the 0 due to the continuity equation, and the only case in this relation remain for the equation is equals to, and we can the final simplification is this relation, or we can have a relation from integration that u y equals to c1 and c2. The two constants are found by applying the no-slip condition at the upper and the lower plate. We have two boundary conditions. At and u equals to v equals to c1h plus c2, and u equals to 0 plus c2, or we can obtain c1 equals to and c2 equals to so with the With replacing to the previous relation, we can obtain a function for the velocity distribution in a Couette flow plus and